everyone, welcome to my YouTube channel. In this video, I am going to explain you one of the important topic from mathematical method of physics, that is special functions. So special functions are kind of functions which are second order derivative and which are homogeneous and linear differential equations. So special functions are very important in case of mathematical analysis or else physical analysis. In mathematics and physics, especially special functions are very helpful. So special functions, if you take like Bessel, Laguerre, Legendre or Hermite polynomial, they consist of power series solution, okay, and generating functions, and also like recurrence relations, and they may consist of orthogonal functions. Okay, we can discuss in detail about them in the next class. So how the power series method is used to get the solution of differential equations, which are second order differential equations, special functions, as we are discussing. So power series method is very helpful to get the solution of special functions. So power series, first we should understand, is a special type of infinite series representing a mathematical function in the form of an infinite series that either may converge or diverge. So power series usually is a infinite series that may converge or diverge. So in mathematics, power series, that is in one variable, the infinite series can be written as n equal to 0 to infinity an, x is the variable, c is the constant. So an x minus c to the power n. If we expand this, we can write a naught plus a1 into x minus c plus a2, so on. So here, as I said, a is what the coefficient of the nth term, an, and c is what constant, called the center of the series. So this is the general formula for power series. So if c equal to 0, the center of the series c is equal to 0, then power series can be written like this. That is only consist of an and x to the power n. So you can expand it. So this is the basic idea about power series. Then here whatever the special functions are there, we are getting the solution with the help of power series. So some of the geometric series, exponential functions and sine functions can be written in the power series form. You already familiar with this. So this is geometric series 1 divided by 1 minus x. We can write using power series method, and you can write the formula. So here is the exponential e to the power x. The power series solution is 1 plus x squared divided by 2 factorial and so on. So sine, if you take sine or cosine is there, then you can also expand it with the help of power series. So these are some of the examples. So let us discuss about the special functions using power series solution. That is what we call Frobenius method. So why we are especially focusing on Frobenius method? The Frobenius method is an approach to identify an infinite series solution of second order ordinary differential equation. So as we are taking the special functions, they are of what? Second order ordinary homogeneous linear differential equations. So then generally the Frobenius method, if you take, it consists of two independent solutions. Okay, any of the Bessel, Laguerre or Legendre, if you take, they consist of two independent solutions. That is the Frobenius method if we want to define. So here first we need to write a second order homogeneous linear differential equation. So y double dash nothing but d square by dx square. Okay, d square divided by dx square. So this is what the second order differential equation, which is homogeneous means it must be equal to 0. Linear means it must consist of order 1. Order 2 degree 1. Okay, and it should not contain any product of the independent variables. So this is what the homogeneous linear differential equation. First we have to write it. Then what we have to do here, if you take it consists of p of x y dash plus q of x y. So p and q are what? The coefficients which should not be constant, which is not possible, okay, in general, to find out the solution in a closed form. Then a common and powerful tool is to find out the solution from series method, that is power series method. As the given differential equation p and q are coefficients, at least one of them is not constant. If it is not possible, then we have to use a power series solution. So first what we have to do here, write down the power series standard formula. Then here y is equal to, we have to write first m equal to 0 to infinity, as we have written here the general formula for power series method. Okay, according to that we have to write y equal to m equal to, you can take m or n. Here m equal to 0 to infinity. So you can write the coefficient constant or the coefficient with c or any one of the alphabet. Cm into x to the power m plus k. Here is the condition c naught. If you put m equal to 0, c naught should not be equal to 0. Okay. First thing, in a given differential equation, take the power series solution for y equal to, then you should differentiate it. You will get dy by dx, y prime nothing but dy by dx. If you differentiate y equal to, that is the power series form, if you take differentiation of x to the power n, you can write it as n into x to the power n minus 1. Okay, so the differentiation of x to the power n. Here dy by dx, if you take, you can write cm as it is, m summation also as it is, m plus k into x to the power m plus k minus 1, like n into x to the power n minus 1. So you have to again differentiate it. You will get second order d square y by dx square. Okay. So for the given differential equation, you are applying power series method. So first you should take y equal to, write in terms of power series form, m equal to 0 to infinity cm x to the power m plus k. Then take differentiation, and again if you differentiate, you will get the values for second order as well as first order. Then how you can get the value of constant k and c. Here we can determine by putting values of y dy by dx and d square y by dx square. So this method is known as Frobenius method. With the help of power series, we are getting the solution of a given differential equation. If we want to have different types of special functions like Bessel, Legendre, Laguerre, first we need to understand ordinary points and singular point. On the basis of that, we can classify. So ordinary points, value of the variable x, where both p of x and q of x in equation 1 are finite. So let us take this as equation 1. Are finite. Then it is known as, they are called as ordinary point. Yeah, I will repeat once again. The value of variable x, where both p and q in equation 1 are finite. If you put value of x, where the p and q become finite, we call them as ordinary points. You can understand with the help of an example. So let us define singular points. Value of the variable x, where at least one p or q becomes infinite, which is called singular point. If you put value of x, any one of the coefficient p and q become infinite, we call singular point. If they become finite, we call that as ordinary point. So let us take example. Here y double dash plus x divided by 1 minus x square y dash plus 2xy. So here this is p and this is 2x is what q. At what value of x the p or q may become infinite? Here when you put x equal to 1 or x equal to minus 1, then the p, if you take x divided by 1 minus 1 is what? 0. That is x divided by 0 you will get. This will be what? Infinite. Then this is called singular point. So x equal to 1 or x equal to minus 1 are a singular point for this differential equation. This is equation 2 we can take. So another example. Here this is p and this is q. You can clearly observe at what value of x the p or q will become infinite. If you take the q here, p is infinite in this case. If you take x equal to 2, then q will become infinite, which is called singular point. At what value of x p or q will become infinite, we call singular points. If they will not become infinite, then we can call ordinary points. Let us take x equal to 3, 4, 5. They are all called ordinary points. Okay, where it will not lead to infinite. Another example. This is p and this is q. So this equation will become at infinite when the value of x equal to 2, x equal to minus 2. You can observe p, if you put plus or minus 2, for p if you put x equal to 2 or minus 2, this will leads to infinite. But q, if you put plus 2 only, then only it will leads to infinite. Any one may become infinite, p or q, or if both become infinite, that are also called singular points. So this is how you can take this as 3. This is how you can differentiate ordinary or singular points. Singular point, if any value of the x, if you put in the differential equation, p and q, any one of them become infinite, then you can identify that those are singular points for that differential equation. So singular points are classified into two categories. One is regular or non-essential. Second one is irregular or essential. So as we know equation 1, the second order differential equation, here in this equation which has a singular point at x equal to x naught. Okay. When this uh, x minus x naught into p of x or x minus x naught square into q of x, both are finite, at x equal to x naught. The point is known as regular or essential. First we should understand definition for that. If this P and Q are finite, then we call them as the regular singular points at x equal to any one of the value if you put finite. If not, then we can call, if P and Q at a value of particular value of x are infinite, then we call them as irregular or essential singular points. Okay. Here in equation this 2 and 3, if we take 2 and 3, the singular points are classified into regular, irregular. Okay. In 2 and 3, if you take the singular points are what? Regular. Regular is what? P and Q must be finite. Okay. And if we take in equation 4, the point x equal to minus 2 is irregular singular point. Why? Because for P it is suitable. Q, if you put minus 2, it will become minus 2, minus 2, minus 4. So that's why it is called irregular singular point. From these examples, we can say that when there is a irregular singular point, the equation doesn't have a series solution. Okay, for this type, equation doesn't have series solution. On the other hand, when there is an ordinary or regular singular point, the equation has series solution. So whether it may be a regular singular point or ordinary, then we can have the series solution for that. So from the given examples, singular points of some special equations discussed in this table 1. These singular points are obviously regular ones. If you observe carefully, the definition for regular or non-essential singular point is quite similar to the definition of ordinary point. So try to clearly understand the definition for ordinary point, singular point first, and then singular points are classified into regular and irregular, and it all depends upon the value of x. At what value of x the P and Q will become infinite. That is very important. So singular points of some equations here in this table we can observe. So these are nothing but the special functions. Bessel equation, Laguerre equation, Legendre equation. This is Legendre, Laguerre equation, Hermite equation. So value of P and Q have been given, and regular singular points also has been given for these special functions. Bessel it is 0, Legendre 1 minus 1 plus 1, Laguerre 0, and for Hermite if you take, it consists of P and Q values. If you observe, it is none. So if the P and Q values has been given, these all are what? Second order differential equations. So you can write easily the differential equation by putting P and Q here. So here are the standard equations for Bessel, Laguerre, Legendre and Hermite. So here the Bessel differential equation is written like this. If you put P and Q, these all are what? Second order differential equations. X square d square y divided by dx square plus x into dy by dx plus x square minus n square into y is equal to 0. In exam or the competitive exam, direct questions will be asked. So try to remember all these four formulas here. Legendre differential equation, if you take 1 minus x square d square, these terms will remain same. Here the value of these coefficients you should remember here. 1 minus x square minus 2x n into n plus 1. Bessel if you take, usually it is x square minus n square. Laguerre if you take, it is having x here and here 1 minus x divided by dx plus n into y. Hermite is quite easy to write. It is d square y by dx square minus 2x dy by dx plus lambda y. So these all are the special functions. In the next class we can discuss about in detail about each of the special functions and their generating functions along with solution and recurrence relations, orthogonality conditions, all those we can discuss. I hope it is helpful for you. Thank you.